Today we can discuss about database management systems module 3, physical data organization. The content in this video will cover static and dynamic hashing. Okay. So what is a hashed file? So hashed file for a DBMS file means it is also known as an external hashing. Okay, if you have given a block of file blocks, and we can divide these files into n equal sized buckets. So we can number it as bucket 0, 1, 2, 3, etc. up to n minus 1. And each bucket will be corresponding to one or a particular fixed number of disk block. And one of the file fields will be said to have a hash key of this file, and the record with hash key value k will be stored inside this bucket I. And where I is equal to, we can get the value of I with the help of the hash function h and h of k. So where h is the hash function. So search, if we want to search for a particular data or a particular tuple, it will be very efficient because it is searching is done according to the hash key. Also, collisions may also occur when a new record comes because there sometimes the hash function will be giving the same value for two different addresses. Okay, so here the collision may occur when a new record hashes to a bucket if it is already full. So the overflow file is kept for storing such records, and the overflow record can hash to each bucket that can be linked to each other. So we can see an example. So here these are the data records, and the hash function will be determining the location of the disk block where the records has to be placed. So we are given the record 1, 2, 3, etc. These are the data records, and these are the data blocks in the memory. Okay. So based upon the hash function, we can decide where these records has to be kept in our memory. So next we have two different types of hashing operations. First one is a static hashing operations, and second one is a dynamic. Okay, static. With the help of this hashing means we need to search the data address directly. That is, we can get the with the help of the hash function or hash method, we can calculate the direct position of the information record on the disk, and without using any of the index structure, index and all. Okay. So here, the main properties these data are kept in data blocks, whose addresses that is produced by the hash function technique. So we need to create a hash function. Okay. So in this hash static hashing, first one, how you can search for a record. Then second, you can see how to insert a record, and third, to delete and update a record. Okay. So while searching for a record, mm, while searching for a record, the same hash function. So whatever the hash function that you are choosing, so that same function has to be used in order to get the address. Okay, and after getting this address, you can search for the address in that particular bucket where this particular the data which you are searching is kept. Next, how you can insert a record. So whenever you want to insert a new record into a table or into a disk, then we need to use the hash key to create the address. Okay. So after creating the address of this new record, and you can place that record in that particular place where you have got the address. Next one is the how to delete a record. So in order to delete a record, first we need to take the record. That is, we need to first retrieve the record, and whatever you have to delete, you first retrieve the record, and the record has to be deleted from the memory, and you that the entry in the hash function, with the help of hash function only, you are taking that, retrieving the record. Okay. Next one is the update a record. So in order to edit a record, again we need to use the hash function, and with the help of this hash function, we need to first find the record and do the necessary alterations or modifications. Okay. Then after doing the updations, we need to add a new record. If we want to add a new record to this particular file, but the address of the bucket formed by the hash function is empty. That is, if it is full, already there are some values inside this address. We can't add a new record to the same field or same uh, location. Okay, that means that there is an overflow. So overflow means there are something inside that, and we are trying to insert a new record to the same position. So that is what we are calling it as a overflow. Okay. So we can see an example that is here. The records, these are some of the records. Okay. And these are the data buckets inside our memory. And these are the addresses, okay, data bucket addresses that we have created with the help of the hash function. Okay. So so with the help of the hash function, we have some of the numbers or addresses, and and according to the hash function only, we are inserting the data into the memory. Okay. So here the data records will be uh, uh, pointing to the buckets or addresses based upon the hash function or hash key value. So in detail, we can see the hash, whenever a hash function is generated by any address that has already contains data, then we can say that the next bucket will be assigned to it. And this process is called a linear probing or open hashing. Okay. So here we have a data record is there. Okay. And there we are using a hash function. Hmm? So according to the hash function, we have the records there. For example, we have a record 3, and we need to calculate the new address where this record 3 has to be kept, and the same that a hash function will be used in order to create this in order to generate the address for the R3. So here we have one, according to the hash function, the generated address for R3 is 110. Okay, so let 110 be the address for R3. So, but if 110 is already full, or some data is already there inside in 110, if that is the case, then what we are doing is that we will be choosing the next address or next location for storing the record 3. So, what is the next location? Here, the next location is 113. Okay, so the next available data bucket will be chosen for storing the record 3. Okay, we can assign the record 3 to 113 because the location 110 is already occupied by some other record. Okay, so this is what you're doing in a linear probing or open hashing. Hmm. Next one is closed hashing. That is, here we have when the data bucket is filled, a new one is created for the very same hash result, and it will be connected to the old one. And this is also known as chaining. Okay, overflow chaining. Here again we are using the same R3 record. Okay, so with the help of the same hash function, we have the address value as 110, right? So here this 110 is already occupied by some other record and it is full. So there is no place in 110. So what you're doing is that we are creating a new record, a new space, and that will also be assigned with the same address, this 110, in order to accommodate R3 here. Huh? But the difference is that we need to have a pointer from the old bucket to the new bucket. Okay, so there will be a chain from these first one, second one. If the third record is also, if another record is coming and that is also hash to 110, then we have to create a new, then we have to create a new record, and that has to be connected with the help of a pointer. And the new, whenever a new bucket is coming, has to be placed, and it has to be connected with a pointer at the end of this list. Okay, so this is actually a linked list type of records. Okay, next type of thing is the combination of these two, that is a multiple hashing. That is, if a program uses a second hash function, and again if the first result is in a collision, Okay, that is a collision means already you have a data inside the hash address. Okay, and if there is a collision, if another collision, then the program will be using a open address and then applies the third hash function and then uses open addressing if necessary. So this is combinations of different hash functions may be used in order to store the records efficiently. So here the static external hash function for disk files. The hashing is also disk file hashing that is done for the disk file is also known as external hashing. Okay, so here in order to see the characteristics of the disk storage, the started address space are made up of buckets. Okay, the address spaces are made up of buckets, and each can hold, if each bucket can hold different records. Okay, so here we have different buckets inside this disk storage, and each bucket can accommodate multiple records. Okay, so what is a bucket? A bucket is either a one disk block or it can be a cluster of continuous disk block. It can be a disk block or a continuous disk block. And what is a hash function? So hash function actually maps the key value to a particular bucket number rather than it assigning to a particular block address. And a table will be maintained in order in a particular file, and this in order to convert the bucket number into the corresponding disk block address. And we will be having a fixed number of buckets allocated. Fixed number of buckets will be allocated for each disk. That is why the name static external hashing. Okay, so now we can see a structure. Okay, so here the buckets and the disk block addresses, how it is. So here this is the disk structure, and that is a cylinder shape. It is represented as a disk structure, and these are the buckets. Okay, this highlighted cells are the buckets, and we have the block addresses. That is, if we have the bucket numbers from 0, if we are having buckets, it will be numbered from 0, 1, 2, 3, etc. up to n minus 1, right? And each bucket will be pointing to the this records. Okay, so here the bucket numbers will be pointing to the buckets where it is stored, actually stored, and each bucket will be having the records. Okay, each records will be stored inside the buckets. So here the block addresses on this disk will be stored in the inside this particular external, and the pointers are used to point the buckets. So in order to reduce the overflow records, a hash file is typically kept about 70 to 80% full. Okay, so reduce the overflow. So normally we won't completely occupy all the records inside this records with the help of this hashing. Only the 70 to 80% will be kept of the records will be kept inside this space. The hash function should distribute the record uniformly among the buckets. Otherwise, the search time will be increased because many overflow records may exist. So the major disadvantage of having this external thing is the first one is we are having a fixed number of bucket space. Okay, here if m is the number of buckets, and we need to find space for m buckets itself, and the file cannot means if you have more number of files or if you have less number of files, the number of bucket size or the number of records that a bucket can contain will not change. Okay, that is, if the number of records in the file grows or shrinks, that won't affect the size of this buckets. Okay, that is because it is static. Again, the ordered access on the hash key is quite inefficient because suppose we need a sorting, which is expensive. That is, it takes time to sort the elements in the basis of hash key. Okay, so here if you have to access the data in the ordering in the base of the hash key order, then it requires sorting. And searching for a record also given for a particular given value for some field other than the hash field. So other than the hash field, if you are searching for a record with a different value or key other than the key hash pair. Okay, then also it is expensive as this key value may not be in a ordered. Okay, it may be a unordered. So this is hash to file, just an overview how this buckets overflow and everything happens with the help of okay, and how we can handle it with the help of chaining. Okay, so what is chaining? Suppose if this is the main bucket, okay, bucket 0 is there, and we have the data 340460, everything is taken here. So the size of the bucket is actually 3. Okay, so here there is no overflow for this bucket. And again, if this is the case in bucket 1. Okay, in bucket 1 means the hash bucket 1 has the values 321 76191. So can you guess what will be the hash function used for these buckets? Can you guess by saying the data values? Yeah, we are using the last numbers. So here this in this bucket, whenever the data value, the last is last significant bit, if it is 0, then it will be going to the bucket 0. And if it is this last bit is units place, if the numbers units place is 1, then it will be going to bucket 1. If it is 2, it will be going to bucket 2. And if it is 9, it will be going to bucket 9. Okay. So here we have the data of 340 and 460. Only these two data are given. So that it will be going to bucket 0. And again, there is no data with that is ending with 0. Therefore, this bucket, there is no overflow for this bucket. Okay, it can hold the two data only. Again, coming to the bucket 1, when in the case of bucket 1, see here there is 321, 761, and 91. So already the three positions of these buckets have three different records. Okay, so the bucket size is 3, and these three locations also filled with some records 321, 761, and 91. Okay, and again, there is another fourth value is coming here. 981 is also coming. So what will we do? That is, here we are using the chain. That is, at the end of this location, a pointer will be pointing to a overflow bucket. Here, this is the overflow bucket. So whenever a new record comes and if the bucket is already filled or filled with the data, then that we can use the overflow buckets, and a pointer should point to this particular location. So here 981 will be stored in this overflow bucket, and finally you will be having the record pointer that is pointing to the null value. Okay. The same for the case of bucket 2 also. Here also we have three values. Already it has three values, and the fourth value, that is 182, is coming here. Okay. So what you are doing is that again chaining. That is 182 is again placed on the overflow buckets, and we will be having a pointer pointing from this position to this thing. Okay. And again it is, again if you are having the again fifth value is coming, right? 652 is coming. So again what we are doing is that, what is it? Again the record pointer from this location is pointing to 652. Okay, and this the final point is pointing to the null. The pointers has to point to each of the records. That is what we are doing the chaining. Okay, so I hope we have discussed in a data structures also this open and closed chaining. The same idea is done in disk database also. Okay. Next one is a dynamic. So here till now we're discussing about the static hashing, where the number of bucket size and the number of records that has to be placed in this bucket is fixed number. Okay. Here it is extensible or dynamic hashed files. So extendable means, what is it? That is, we can it is able to grow and shrink the data, right? The bucket size can be made it bigger, or it can also grow smaller. The shrinking of the number of file records can be done dynamically. We can hash techniques are adapted to grow the dynamic growth and shrinking of the number of file records. And this techniques, following techniques are the which are using the dynamic tech is the dynamic hashing, extendable hashing, and linear hashing. Okay. So the both the dynamic as well as the extendable hashing uses the binary representation. That is very important. So here, whenever you are given a data, it has to be converted into binary representation. And based upon the binary representation, we have to create a hash value. Okay. The hash function will be based upon the binary representation of the data. Okay. So here hash value h of k in order to access the directory. Here there is another term called directory. You can see next slide. So dynamic hashing, in dynamic hashing, there is a directory which is a binary tree, as well as in extendable hashing, the directory means it is the data structure used for directory for dynamic hashing is binary tree, whereas the directory which is used for extendable hashing, the data structure is array, the symbol array of size 2D. Size means two dimension length of the array. It is 2D. What is the value of D means? D is a global depth of this uh, global depth. Okay. So what is the global depth? What is this directory? Everything we can discuss the terms. Okay. So what are the in dynamic hashing approach? It will be it is used to solve problems like that is the bucket overflow. Okay, so because if you have static means the number of records that can contain the a single bucket will be always constant, right? So here that we can change it up dynamically. As the number of records increases or decreases, the data bucket grows or shrinks in this manner. Okay, that is what, so therefore, without causing any performance issues, that can be done in this dynamic hashing. So next we can see what is extendable hashing. Extendable hashing is also a dynamic hashing method wherein directories and buckets are used to hash data. So here we have a new term called directories, and it is aggressively flexible method in which this hash functions also experience some of the dynamic changes. So the main features of this extendable hashing is that we have directories. So what are directories? So directories are actually, we are used to store the address of the buckets in pointers. Okay, so directories will be storing the address of the buckets. Uh, uh, so here we actually this will be storing the pointers, right? Address means the variable which is used to store pointers, and ID is assigned to each directory, which may change every time when the directory expansion takes place. So here we have seen that we can in extendable hashing the growing and shrinkage is possible, right? So in some cases this directory can expand. Okay, so when this expansion is taking place, so here this directory is assigned to each directory or each record or each cell will be assigned to a unique value ID, and that will also change when the expansion takes place. Okay, what is a bucket? So bucket actually that are used to hash the actual data. Now we can see the representation when and with the help of the representation it will move clear. Okay, so this is the representation of extendable hashing. Here, the highlighted thing. This is the directory. Okay, directory and the global depth of this directory is. So we have discussed, right? We have to have a in extendable hashing. The data structure is a what is the data structure? It is a array, right, of 2D, where D is the global depth. So global depth means it will be the depth is equal to 2. So here the unique ID will be having a 2-digit number. In dynamic hashing, we have to use a binary representation. So we have 2-digit numbers, that is 2-digit representations, that is 00, 01, 10, and 11. Okay. So what will be the possible values? That is the number of directory values will be 2 raised to d values, where d is the global depth. Okay, that is here the global depth is 2. So, therefore, here the global depth is 2, right? So here 2 raised to d means what is d? That is d is equal to 2. So 2 raised to 2. Okay, so which is equal to 4. So therefore, the total number directories can have total that records, number of records a directory can have is a 4 number of records. Okay. And here this is local depth. So here this how many datas this record can contain. So this is local depth for each record. Okay. So here the can contain up to 2 records. Here also it is up to this is local to the particular bucket. Okay, bucket. Okay, these are the buckets. How many records each bucket can contain? That is the local depth. I hope it is clear. So this is actually here, in this case, the local depth given as 2, right? And the local, sorry, global is given as 2 and the local is given as 2. Okay. Now we can see the, how the extendable hashing structure will be looking when the global depth is 3. So when it is 3 means 2 raised to 3, right? 2 raised to 3. So 2 raised to 3 means it is equal to 8. So here the number of directory pointers having the number of directories will be 8. So since we are using the binary representation, it will be given as 0 from 0, 0 to 1, 1. Okay. And we will be having the pointers pointing to the each buckets. So what will be the number of buckets? For that, sorry, number of records in a bucket, number of records. This is a single bucket. Okay, this is a single bucket. This is a bucket. This is a bucket. This is a bucket. And we can have the records. So that the number of records that each bucket can contain is defined by the local depth. Okay, the local depth of each bucket is given here. That is D dash. Okay, so here this is the bucket 0 with local bucket value, sorry, local depth value as 3. So the number of records here it can contain is 1, 2, and 3. Okay. If you are looking for this thing, here the local depth is 2. So here the bucket records can be having 2 values. Okay. Here this can take the 2 number of records. Okay. So here the hash value. So the address has to be taken as also 3 values. Okay. The bucket for records whose hash values should start with 3 different values. Okay. Okay, so MSP is least significant which we are taking. Okay. In this case, that is this point is pointing to the second bucket. D dash is equal to 3. So here we have to take the three units. That is the 3 bits. Okay. So here 0, 0, the hash value that will start with 0, 0, 1 will be assigned to this bucket. The records having 0, 0, 1. What will be this case? So here we are looking only for the hash value that starts with 0, 1. Okay. So 0, 1 means here this is the case. 0, 1 is there. Again 0, 1 is this is also the case. So here whatever the data that is 0, 1 and 0, 1, these both data will be given to this bucket 0, 1, 0, 1. Okay. Here also here the value is 1, 0. 1, 0 means the data is this thing 1, 0 here, and again there is 1, 0. Okay. So the data that starts with 1, 0 here from this thing, and from the both pointers are pointing to the same bucket where d prime is equal to 2. Okay. Here all this number of bits taken is 3. Here this is also 3. Now I hope it is clear. So here this is a directory, and we can set the number of entries for the directory. So if the directory the depth is equal to the number of bits that has to be taken is 2. The directory depth is equal to 10. Then 2 raised to 2. That is, there will be only 4 entries. If it is 3, then we can have 2 raised to 3, that is equal to 8 entries. Global depth is equal to 3. And this is the local depth given for each bucket, and it can be it is not necessary to have the same values for every bucket. Here, if you are if you can see that this bucket is having 3, the local depth is 3, whereas for this bucket it is 2. That is also okay. So this means that we are taking the first 3 bits of the data. Okay, so based upon the first 3 bits, we will be assigning the data to this bucket. So this we can discuss in detail with the help of an example. Okay. So these are the basic mm, definitions and all. What is a directory? That is, directory means we, in order to store the pointers to the buckets, a unique ID will be given to, and this ID will change when there is an expansion is taking place. So here, and the number of entries is directories is given by 2 raised to global depth. And what are buckets? Buckets are usually used to store the hashed keys, and the directories will point to the buckets. The buckets may contain more than one pointers based upon the local depth. And there is a condition that the local depth should be always less than or equal to the global depth. It will not be never greater than the global depth. Okay. Global depth is what is the global depth? That is the number of bits in the directory ID. Local depth also here it will be always less than or equal to the global depth. What is bucket splitting? That is when an element, when the number of elements in a particular bucket exceeds a particular size. That is, it has whenever a bucket size has come to a maximum limit, then the bucket will be bucket is splitted into two different parts. That is what you're doing in a bucket splitting. And what is directory expansion? That we have already seen that in a unique ID will also change during the expansion, right? What is expansion is that whenever a bucket overflows, okay, when a bucket overflow takes place, the directory expansion is performed. And when the local depth, when the expansion is performed, the condition, the case is that when the local depth of the overflowing bucket is equal to the global depth. Because if the local depth of the bucket is 2 and the global depth is also 2, then the bucket expansion takes place. If it is less than, that is, if it is this one is 2 and this is 3, then the expansion does not take place. So this we can see in the next few slides, that is when we are doing an exam. Okay. So this is the basic working. We can discuss the basic working of extendable hashing with the help of an example. So here, first we have to take a data. Okay. So we have to consider a data. So the things that you have to remember is that extendable hashing is done on binary representation, right? So when you get a data, you need to convert it into binary representation. So first we have to analyze the data, and now we are currently using integer number. We can map any type of data, whether it is integer or everything can be done. Now for you can choose a integer number. Okay. So I have chosen a number 49. Okay. So here the input data given is 49. What is the second step? Second step is that we have to convert this data into. So now we can say the basic working of the extendable hashing. So here we have a data given here. So the data given, we have to convert it into binary because binary representation is required for extendable hashing. So the given data is, let it be 49. Okay. So we need to analyze the data, and then again we need to convert it into binary format. So here the binary format of 49 is given as 110001. Okay. Next step is we need to check the global depth of the dictionary directory. Okay. Sorry, here we have the global depth of the hash directory is 3. And identify, now next we have to identify the directory. So considering the global depth, which is equal to 3, and you are given the binary representation, that is 110001. Okay, so we the hash function considered is that we will be returning the last LS base of this binary representation of the given data. So here the f of x, the hash function we are considering is that we have to take the last 3 bits. That is the three last significant bits. Okay. Hash function will return the 3 LSBs of 11 00 01. That is last, this is 001. So this is the value. Okay. Now we need to navigate into the bucket, and the directory ID is the directory ID is having 001. Okay. So the directory location, we have found that the directory ID is 001. So now we can insert the element and check whether the bucket is full or not, or that is a bucket is overflowed or not. If it is overflowed, then if it is not overflowed, then directly we can take the data and store it in the corresponding bucket. Okay, that is the case. And if an overflow occurs, then there are two cases that has to be considered. That is if there is overflow, as well as if the local depth is less than or equal to the global depth. Okay, that is, what is global depth? Global depth is global depth is D. Okay, and local depth is D prime. So D prime should be less than or equal to D. Okay, then we have two cases are there. First case is if the local depth overflowing bucket is there, and if the local depth is equal to D prime is equal to the global depth D, then what you have to do is that we have to do the directory expansion, as well as we need to do the bucket splitting. Okay, bucket split as well as directory expansion. Okay, and again, after doing these two things, we have to increment both the values. That is the global value, global depth value, that is D value, and the local depth value, that is D prime value, by 1. Okay, so if it is 2, then both will be 2, right? It is equal. Then both has to be incremented to 3 as a 3. And again, you assign the appropriate pointers to the pointers from directories to the bucket. So next case is that the local depth, that is D prime, is less than global depth, that is D. If that is the case, then we have to do only the bucket split. Okay, no need to do the expansion. Only bucket split will take place, and you increment only the D prime value, that is the local depth by 1. So if the local depth is 2, and if the global depth is 3, okay, 2 is less than 3, then that is the case. Then you have to increment the local depth D prime by 1. So here it will come as 3. That is D prime will also will be coming to the same value in this case. Okay, it is not necessary to have the that is one difference value. Okay, so we can consider an example. So here we have a key values. Okay, classification of keys into buckets based upon the hash address prefix. So you are given some values, key values, and after for values you are given some addresses also. So this is the input. Okay, so we are key values and hash addresses are given. So based upon these values, you have to do the dynamic hashing or extendable hashing. Okay, so if you are, we can see that the last 2 bits of this one, number 1 is 10 and 3 is also 10. Again, so we can take the these two values. Here we have, that is D prime value. This number of records in a bucket be 2. Okay, so therefore we are checking only the last 2 numbers of this thing. Okay, so since D prime is equal to 2. Okay, so these 2 will belong to a particular bucket. Say if it is bucket 1. And again, we have the second number, that is the key number 2 as well as key number 4. So here in this thing, this is 00 and this will also 00. That also will be coming to us. So here we can say that the key value, this thing, and here this will be going to a bucket B0 or B1. Here 2 and 4 will be going to B0. Since the bucket numbering is will start from 0 till m minus 1. So the first bucket we can say it as B0 and second bucket is B1.
and likewise by 2, B3, etc. up to Bm minus 1. And next, what about the next bucket? So we have these three values. Again, this then 5 and 6. 5 and 6 will be going to the bucket B2. Okay. And again, the last value 7, we have the bucket number 3. Okay. So B0, B1, B2, and B3. So this is how we have to assign the hash values, hash addresses to a bucket values. Okay. So this is the case. Okay. So we have these values and how it is done. Here, this is the representation of data buckets. So here the last two records, last two values, this will give you the ID, director's unique ID is there. So last two values 00, 01, 0, 10, and 11. Okay, 00 is having the key values 2 and 4. So 2 and 4, there will be a bucket holding these two records, 2 and 4. This is bucket B0, and the directory, inside this directory, there will be a pointer which will be pointing to this data bucket that is represented here. Okay. For bucket 1, it will be holding 5 and 6, having the values. The last two bits of 5 and 6 is 0, 1. 0, 1. Here also 0, 1. So 0, 1, the unique ID, descriptor ID 0, 1 will be the pointer from this 0, 1 will be pointing to the bucket B1, which is holding the numbers 5 and 6. Similarly for 1 and 3, B2. And the last number here, this is a bucket B3, which is holding only a single data, that is 7. Since the 7 is only having only number, we have the values 1, 1. Okay. So therefore, it will be this bucket will be containing only a single value, that is 7. Okay. Now we are trying to, so here this is the case and there is no collation. So this is done in normal case. Now we are trying to insert a value number 9 with address, hash address 10001. Okay, so here in this case, when 9 value is having the hash address 10001, right? So the last two numbers of this is 01. So 01 means the ID, unique ID is 01. So which is pointing to bucket 1. So already in this bucket, there are two records are there, 5 and 6. So it can't hold 9, right? Now the overflow occurs. So we need to check for the condition. What is which case we have to take? So when an overflow occurs, we need to check for two cases, right? The first cases is, that is, if we need to check whether the D prime value is less than D or the D prime value is equal to D. So which case is this? Which case is this? This is here the D prime value is equal to 2 as well as the D value. That is the D prime value means the number of records is this thing. Okay. D prime is local depth is 2 as well as the global depth is also 2. So this is the case. So when it is equal, then you have to do two things. That is both the splitting, bucket splitting and the expansion, that is directory expansion is also to be, has to be done, and increment the value of depth by 1. So here it is 2, right? This is also 2, this is also 2, and increment the value by 1, that is D prime is equal to 3 as well as D will also be equal to 3. D prime is equal to 3 and D will also equal to D. D is equal to D prime is equal to 3. So when it D prime is equal or D is equal to 3, then we need to expand the directory, right? By 3 bits. 3 bits has to be used. So here, say 3 bits, how many records will be there? Data records here. If you are using 3 bits, then 2 raised to 3. That is, it is equal to 8. So it will be starting from 000, from 000 to then 111. Okay, 000, 001, likewise. Okay, so this is the case. So next one is that, so here, okay, so we have expanded our data records here. from 0, 0 to 1, 1, 1. And this is the buckets. Now we are trying to insert the number 9. Okay. So number 9 is having the hash address is 10001. So 9 is having the address 10001. So here, when you are looking into the last 3 bits, okay. So here in this bucket V1 is splitted, right? So last 3 bits of 9 is 0, 0, 1. And what about 5? 5 is also, so 5 is also having this here. 5 is also having 0, 0, 1. And 6, it is 1, 0, 1. Okay. So here, both 5 as well as 9 is having 0, 0, 1. The last 3 bits, 0, 0, 1. But in the case of 6, it is having the last 3 bits is 1, 0, 1. So we have to remove 6 from this bucket 1, B1. And you have to place the number 9 here. Okay. Because both 5 as well as 9, the last number is 0, 0, 1. And we need to have a pointer from 0, 0, 1. Data record 0, 0, 1 has to point it to this particular bucket. Okay, 5 and 9. And we have pushed the data record 6 to a new record having the number that is 101. Okay. So here in this case, we have to see that only the bucket B1 has splitted. Okay. So here in this case, the B1 record has splitted, and here the local depth of this bucket D prime is equal to 3. Okay. Whereas in this case here, the D prime is equal to still it is 2 only. Okay. Therefore, the data here we are only checking the last 2 bits of 2 and 4 only. Okay, that is last 2 bits of 2 and 4 is still, again, it is still 0, 0. Okay. So therefore, it will be pointing to this bucket. Here also 0, 0. So this pointer will also be pointing to the same bucket because the D prime is equal to 2. Here it is 3. So only we have to look for 0, 0, 1. Then only the pointer will be pointing to 5 and this bucket B1. What about the case bucket B2? B2, the last two bits is 1, 0. So 1, 0, the direct unique ID 1, 0 will be pointing to 1, 3, the bucket B2, as well as again 1, 0 is here. Okay. Here also the pointer from this thing. So pointer from this thing and pointer from this thing. That is 1, 0. Here also 1. Because B2, the D prime of B2, bucket B2 is still, it is 2. Okay. So we are only taking the last 2 bits. Therefore, the record 1 and 3 will be still in a bucket B2. And 7 is also, we are looking for the last 2 bits, that is 1, 1. So 1, 1 is only in this direct ID, only this field is having 1, 1. Therefore, this well as well as this thing. Okay, so here both this 2 records will be pointing towards the bucket B3. Okay, and finally 6. 6 is having the number is 0, 1. Okay, 0, 1 will be pointing to the last bit is 0, 1. Therefore, 0, 1 will be pointing to this. Okay, the new bucket B5. Okay, so this is all about the extendable hashing. Hope it is clear. We can discuss about the